Okay, in this third and final video, I'm going to talk about part 3 of your CAPT Crash Course. Carbon cycle, combustion reactions, greenhouse effect, acid rain, brownfield sites, energy generation, pros and cons, energy generation here in Connecticut, and I'll end on population pyramids. So, I think I learned my lesson from the rock cycle and the tectonics, where instead of trying to draw something, I'm just going to show a picture from the internet. So that's probably not that clear, but this is trying to show the carbon cycle. So let me sort of talk through this. Carbon takes many forms on the planet. Probably the most pertinent one right now is carbon dioxide up in the air. So here's your CO2. Now, carbon enters the atmosphere and exits the atmosphere back into the ground in a few different ways. We show vegetation here. Basically, plants and certain, like funguses, will pull carbon out of the atmosphere, photosynthesis. We have carbon that will naturally kind of hit the ocean and just sort of go into it. That's just a natural process that occurs. At the same time, there's dissolved carbon in the ocean that's going to hit the surface and rise out. And again, at the same time as plants are taking in carbon through photosynthesis, they're also releasing carbon when they die, and that decays. The major sort of holding places, and major carbon sinks we call them, are in the deep ocean. Now the unit here is, I can't even read that. GTC, I apologize, I'm not sure what the unit is, but we can at least use this as a relative way of seeing this. So in the atmosphere, there's 750 units of carbon currently. Down in the deep ocean, we have 38,100. Now, the vast majority of that is the little shells of small plankton-type organisms that are made of calcium carbonate. A lot of carbon gets locked up, and it kind of sinks to the bottom, and it kind of actually builds limestone, which is a type of sedimentary rock down there. So there's a lot of carbon just stored at the very bottom of the ocean, just sitting there. Sediments, 150, and there is also carbon stored within the crust and the mantle of the Earth. Now, what's eventually going to happen to all this carbon at the bottom of the ocean is that the bottom of the ocean is slowly crawling towards land, and it's going to subduct down into the crust, basically. Now, as that carbon basically rides into the crust like a surfboard, it's going to melt, and it's going to end up as in the form of magma, and it's going to erupt out of volcanoes. So let's see, did they include volcanoes on this one? I'm not seeing it, but volcanoes actually release a lot of carbon dioxide when they go off. Now, fossil fuels, current cement production, 4,000 units, so obviously we're certainly contributing our share to that, and that's sort of what I'm going to talk about next. So just with the carbon cycle, it's important to notice that carbon is cycling around the planet. It's not just in the air like you might think. So, combustion reactions. This is something we've covered in chem, so actually it should go super quick. Combustion reactions, you have your hydrocarbon plus O2 gas yields CO2 plus H2O. Now, hydrocarbon is just a long chain of hydrogens and carbons, and examples of hydrocarbons are coal, oil, and natural gas. Now, wood is also a hydrocarbon. I should mention that too. Basically, all plant life and all animal life is hydrocarbons. Now, for a long time, humans have been burning wood for 100,000 years, or someone could quote me on a better number than that. Our society is built around us being able to burn wood for heat. That's the reason that humans were able to go all over the globe and cross into North America on that natural land bridge, during the last ice age. So humans have been burning wood and producing CO2 for quite a long time. The problem is we didn't really start burning these until a couple hundred years ago, the start of the Industrial Revolution, and more specifically in just the last 100 years, it's really been huge how much humans have burned. And honestly, I mean, it's a good thing. Like, society has taken off because of it. We basically found free pockets of stored energy that have been just waiting for hundreds of millions of years to be utilized, and we found them and we utilized them. The downside is that one of the products here is CO2, which is a greenhouse gas. Carbon dioxide in the atmosphere does trap heat. So let me go over the greenhouse effect. Now the greenhouse effect is named for a greenhouse, which is basically, try my best rendition here. Looks like this. And you have plants growing inside. And you generally have sort of windows that open up here and sometimes vents down at the bottom. And the idea is that sunlight shines through, and this house is usually made of plastic or glass. Sunlight is able to shine through, heat up the plants, and then heat leaves those plants but gets trapped. And it's important to note, this is probably the most important thing that a lot of people don't really realize. Sunlight is different from heat. Sunlight has a different wavelength. Generally it has a shorter wavelength, which means it has a lot more energy. Heat has a slower wavelength, means it has less energy. Heat kind of is like this. There's a difference, and that difference means that sunlight can penetrate a lot of things without any problem at all, like glass and clear plastic. Heat, however, cannot. Now look, eventually heat makes it through. It's not like your car gets hot and it's hot forever, but it takes a long time, and that heat's going to bounce around like this and bounce off the walls. And that's the whole idea behind a greenhouse. You can grow plants in the winter or in the very early spring and late fall, even when it's cold outside, because that sun is going to heat up that greenhouse. Now the same thing happens, but instead of a greenhouse, it's the earth. So imagine here's Earth's surface. Okay, here's the sun, and it's shining very high energy sunlight down on Earth. Now that sunlight gets absorbed by the Earth's surface, whether it's by the oceans or by the forests. Now some of that does bounce off if it hits something really reflective like snow or ice. Now that's actually one of the problems, is that when our ice caps melt, it means more sunlight's going to hit the Earth and stay there. But anyway, it's going to hit the Earth, and it's going to radiate out as heat. Radiate out as heat. And there's a difference here, because sunlight can pass right through the Earth's atmosphere. Now the atmosphere, we talked about that during gases. The atmosphere is just the gas particles that are trapped around Earth, and they're there because of gravity. That's the reason it just doesn't float off into space forever. So all these little air particles are throughout the atmosphere here. Now, sunlight can pass right through them, right through all of them. Sunlight can't really be absorbed. Well, I should say it generally passes right through. There are certain things like ozone that do absorb sunlight, and they actually absorb the UV radiation, which is the dangerous kind, and it kind of breaks up the ozone, which is O3. But anyway, the important thing I'm noting is heat gets trapped by certain air particles. Sunlight passes through the vast majority of it. So this atmosphere here contains a lot of different gases. 99% of them fall into two categories, O2 and N2, nitrogen and oxygen. It's like 78% nitrogen, 21% oxygen. Fortunately for us, these are not greenhouse gases. Now, when I say greenhouse gases, I mean gases that trap heat. If these trapped heat, we would not be here right now, because this planet would be thousands of degrees. It'd be like Venus. Now, there are certain gases in here that do absorb heat. CO2, CH4, H2O. These are gases that do absorb heat, and these are known as greenhouse gases. So when heat hits CH4 or CO2 or H2O, it's going to get absorbed by that and then re-radiated out in any random direction. It could be up, it could be to the side, it could be down. So what you end up seeing is kind of the same thing you saw in that greenhouse, where sunlight's able to go right in, but heat gets trapped. Now look, eventually it gets out. eventually that water is going to radiate it up. This carbon dioxide radiate it up. And, that's why the Earth just hasn't been slowly heating up for the last 4 billion years. Heat does get out, but the thing is it kind of lingers around here for a little bit before getting out. And this is good. If there were no greenhouse gases, the Earth would be like the moon or it'd be like Mars, where it'd just be way too cold because all the sunlight would just bounce right off. Or even the heat, I should say, would just radiate out and just go into space. If the greenhouse effect weren't here, we would not be here. However, the problem is in the last 200 years, with all of our combustion reactions, we have been producing more and more CO2. Now, there's still not that much CO2 in the atmosphere. Originally it was something like 270 parts per million, meaning only 270 out of every million molecules in the atmosphere was carbon. The thing is, it's solid science. It's been known for decades and tested over and over again that carbon dioxide does in fact absorb and re-radiate heat. And our amount of carbon dioxide has gone up by 30–40%. Let me actually check what the actual carbon level is right now. 400 ppm milestone. Oh, here's Earth CO2 homepage. (404.16 parts per million). Now, for the longest time, it was right around 270, 280, and then humans really took it up. And we know that CO2 gets absorbed, or I should say heat gets absorbed by CO2. And we can even look at like Venus, where Venus's atmosphere is mostly CO2. And that actually happened because they have so much more intense volcanoes. Last video I said volcanoes release CO2. Well, Venus, with all its volcanism, has atmosphere filled with CO2, so it really traps heat, and that's why Venus is just a giant fireball, basically. We can also look back in the fossil record, not really fossil record, but deep in ice cores, and we can correlate the level of CO2 concentration to the temperature at the time, and it correlates very nicely. People claim there is still a debate on whether this science is true. That debate is pretty much over at this point. If you want to argue on CAPT that climate change isn't happening, you can, but have some facts behind you. So that's the greenhouse effect. Let's talk a little bit more about pollution and acid rain. Now this is a separate issue from greenhouse effect. So this is going to come into play later when we talk about coal especially. Coal gives off a lot of sulfur and nitrogen oxides. Now I wrote SOx and NOx. The X could really mean any number. For sulfur oxide, it's generally SO2 or SO3. For nitrogen, it could be NO, NO2, NO3. So instead of writing all these out, we could sometimes just categorize it as SOx and NOx. Now these are two pollutants that get released a lot of times by industry and by power plants, mostly coal. When these enter the atmosphere, these are gases. When these enter the atmosphere, they react with water and they form acids. So here, this sulfur oxide, let's say we have SO2 plus H2O. That's going to form some sort of sulfuric acid. Now, I mentioned acids in a couple videos ago, so that's going to be H2SO4. And let me see if I could quickly balance that. Oh, we'll leave that for later. But anyway, these are going to react to form sulfuric acid, and same thing, HSO3 could form the same type of sulfuric acid. For nitrous oxide here, we're going to get something like perhaps NO3 plus H2O is going to form HNO3. But the point is, these pollutants, these SO2, SO3, NO2, NO3, they're going to enter the atmosphere and react with water. So instead of raining down water, we're now raining down acids. Now, it's not like it's 100% acid just starts falling out of the sky, but it gets to the point where there's enough acid in the water that's falling to actually have an effect. Now, The cutoff for acid rain, I haven't looked it up in a while. I believe it's something like a pH around 6 or so. But something that you should keep in mind is that natural water is naturally acidic a little bit, something around a 6.5 on the pH scale. But remember, a pH scale is logarithmic. So if you go from something like a 6.5 down to a 6, or let's even say a 5.5, from 6.5 to 5.5, you've become 10 times more acidic. And that might not really affect us humans because we have society and raincoats and roofs, but it really does affect plant life a lot. Let me just pull up some pictures of forests affected by acid rain. So there's some pictures here. You can see it's just kind of bare trees. And this isn't like, just certainly not like one rainstorm just kills a whole forest, but it's just kind of chronic rain falling, acid rain falling will do this. And it also affects aquatic life too, like fish. And that's because, as this acid rain falls, it's got to go somewhere, so it will either roll downhill or it'll sink into the groundwater and travel, as groundwater into these lakes and ponds. And it kind of accumulates, and the more acid that you get entering this, the more acidic the water is going to be. And fish and plants, they're a lot less susceptible, a lot more susceptible, I should say, to acid than we are. So acid rain is a problem. You don't really hear about it too much now, and that's kind of thanks to government regulations on sulfur and nitrogen oxide emissions. So you guys probably did an acid rain lab in biology. I don't have that up just yet, but try to think back on what you did for that. I want to talk quickly about brownfield sites. Brownfield sites. Basically, brownfield sites are locations where some sort of building, some sort of company had some kind of environmental problem happen. Something leaked, something spilled, whether it was one giant leak or whether it was a little bit leaking over decades. Some kind of chemical problem with the ground. The state will identify it, and after the company shuts down or something like that, whether they shut down voluntarily or whether they get fined into oblivion, basically, the site now is just a vacant place, contaminated. Now, if you're a company thinking of moving somewhere, why would you ever want to go somewhere that's contaminated? You wouldn't. So the state sets up something called brownfield sites, and it will basically subsidize the remediation of that ground. So the key word here is remediation. So the state will help you pay for the cleanup. Remediation means to clean the ground up. Now that could be, a lot of times they use certain kind of plant life, phytoplanktons, biology is not my strong suit, but certain types of organisms that will kind of absorb the chemicals, certain types of algae, things like that. Other things, they can go in and kind of filter out the groundwater, things like that. So the state will help pay for that, and that kind of benefits in a lot of ways, because you say, well, why are we wasting tax dollars on this? But if you think about it, first of all, do we really want a poisonous, hazardous waste site in the middle of a town? No. And second of all, by utilizing that land, you're allowing a business to move in and kind of benefit the tax base. So this is just kind of a seemingly random thing, but the state likes to put it on the CAPT test, brownfield sites. Generally, big box stores like Home Depot and Walmart love to take advantage of brownfield sites because it's kind of win-win. They get sort of a tax break. The state helps pay for the remediation, and then the city gets a nice place where people can shop and spend their tax dollars. Money goes back to the town. So that's brownfield sites. Next thing I want to talk about is sort of the pros and cons of different methods of energy generation. Now, in the last video, which was electricity, I talked about how most types of electrical generation are the same. It's the same concept. We call it electromagnetic induction. And the idea is you take a coil and a magnet, and if you could just move the magnet or the coil relative to one another, assuming that coil is hooked up to some kind of, house, all you need to do is get some kind of movement here, and you can generate electricity. And this is the basics behind most types of electrical power. For wind turbines, it's just wind will cause that coil to spin. For water, hydroelectric, water will cause it to spin. For coal, oil, trash, nuclear, natural gas, you're using steam generation. You basically use that heat to burn water, to heat up water, to create steam, to spin that turbine. So I'm going to talk in a little more detail about some of these methods, talk about some pros and cons. So I'll start with coal. Now, I'll start with the cons, because that's the one that most people kind of come up with. The cons. Well, the big con here is CO2. Coal is really the dirtiest source of oil in terms of carbon emissions. 1 unit of coal produces the most CO2 out of any other sort of source of energy. It also releases SOx and NOx. I mentioned that earlier. Coal power plants are one of the big reasons we had acid rain. And government regulations kind of have kept that under control, but they still release sulfur and nitrogen oxides. There are other pollutions involved in the burning of coal too. A lot of mercury gets released, so it's kind of a lot of pollutants like that. It's dirty work just mining the coal. This was always a stereotypical job where, guys would die in the coal mine all the time, and if you were lucky to survive till you were 40 or 50, well, you'd die of black lung. Now, it's obviously a lot cleaner now. We have more technology, but it's still a dirty job. It's still a dangerous job. And the methods they use now, like mountaintop clearing and strip mining, it really affects environments as well. So it's an environmental problem too. See what I can say for this, for coal. There is a high cost of transportation because it's not liquid or gas, so you can't transport it through a pipeline. You have to put it on a train or a truck and ship it. So I'll say transportation. So there's a lot wrong with coal. So you might think, well, why would people still like coal? Well, the big pro that you have to consider: cheap. It's cheap and it's abundant. There's a lot of it. Cheap and abundant. Right now, about 55% of this country is powered on coal. Another thing we can mention is that it is homegrown. Well, homegrown, not really, but it comes from the U.S. We have a lot of coal mines here in the U.S. We might import some. It just might make sense economically. Canada has a lot of coal. But it's grown. We mine it right here in the U.S. and generally pretty locally too. So these are the basic pros and cons of coal. I guess I should mention coal comes from basically dead plant and animal life from hundreds of millions of years ago. And this actually brings up a big con that I almost forgot to mention, is that it is non-renewable. And you might say, well, wait a minute. When everything on the planet today dies, it goes in the ground, doesn't it turn into coal? Well, yes, but it takes hundreds of millions of years. And basically, the coal that we've been using is like 200 or 300 million years worth of coal all being generated. And we've used it in the course of like a couple hundred years. And it is non-renewable. Estimates put it at somewhere around 100 to 150 years of coal left at our current rates. So the idea is, obviously, as that gets less and less and less, the price is going to go way up, and that's going to drive other sources of energy down in price. So that's coal. For oil, I mentioned earlier, oil is not very commonly used for electricity generation. It's a lot more used for home heating oil, which is what goes in your furnace, or it's used refined into gasoline and jet fuel. But with oil, it's very similar pros and cons to this. It does release a lot of CO2, though not as much as coal. It's about 1/3 cleaner per unit. A lot less SOx and NOx. Transportation is a little easier because you can put it in a pipeline. Keystone Pipeline, you probably hear about on the news, that would transport oil from Canada down into the U.S. Oil is non-renewable as well. Same thing, it formed from plant and animal life. And current estimates say anywhere between 40 and 70 years of oil left, and that all depends on how much we use. The pros of oil, I know I have coal here, but it's very similar. Oil is not quite as, well, right now it's pretty cheap. That's why gas is so cheap. But oil is generally cheap as well. It's tough to quantify coal versus oil because, like I said, they're kind of used for different purposes. But oil is pretty cheap. And in fact, in terms of like what they say BTUs per pound, BTU is like the British version of joule. So in terms of like joules per gram, oil packs the biggest punch out of anything except pretty much uranium. In 500 years, people are going to look back at us and say, man, they had oil. They had the best source that it flowed out of the ground. And, you could take 1 gallon of gasoline and power a giant car to go 30 miles. It's powerful and it's energy packed. Homegrown as well. Not so much in the past. Most of it generally came from the Middle East, but we've found new ways to get it from, the Gulf of Mexico, and Texas right now is booming in oil. So definitely not so much abundant with oil. Next one I'll talk about is natural gas. Okay, so let's do cons and pros. So the con is, again, CO2 emissions. I mean, natural gas is pretty much CH4. It's like 90% of it is methane, and then there's other kind of gases in there, a little heavier. So natural gas isn't like a compound. It's more of a mixture, which is mostly carbon tetrahydride or methane. It does release CO2, but it's only about half as much as coal, so it is a little bit cleaner. It's pretty easy to transport. It can be transported. They can either kind of compress it and liquefy it, transport it in a truck, or they can transport it through like some kind of pipeline. Natural gas is pretty cheap, especially now with fracking. Fracking is basically companies can pump chemicals into the ground, which kind of loosen up the layers of bedrock and kind of allow pockets of gas that were originally inaccessible to now be accessible. And it's really been good for the industry. It's one of the reasons energy is so cheap right now, because, well, first of all, there were a lot of like gas mines where they would drill into the ground and start collecting gas that would come out of the ground, and then it would get to a point where the gas started to get less and less and less, and someone ran the numbers and said, we're collecting $1 million of gas every month, but operating costs are $1.5 million a month. So they say, all right, time to move on. So they close up the gas and they move on. Well, now with fracking, with this new technology, they can go back to some of those old places and pump these chemicals in for pretty cheap, and they get a whole lot more gas coming up. So it's good in terms of abundance. So I'll even say abundant. And homegrown. I mean, a lot of natural gas exists in Pennsylvania, Ohio, New York, until they kind of cut down on fracking. So I will say homegrown. The cons, though, there are a lot of cons sort of associated with fracking itself. Well, before I mention that, it is non-renewable. Same thing, it's a fossil fuel. It came from dead plants and animals, and estimates put it at around 150 years or so left. That was as of a couple years ago. Right now, the whole world is booming in production and use of natural gas because of fracking. And it's probably going to run out sooner. But anyway, let's talk about the fracking. Now, fracking stands for hydraulic fracturing, meaning they use a pump to kind of get inside those cracks within the earth and get that fluid out, or the natural gas and some oil out too. So some of the problems we see with fracking are that these chemicals can occasionally leak into people's water, especially well water. Also, since it kind of breaks up the bedrock and allows gas to move underneath, gas has been reported to get inside people's tap water. In fact, if you just Google something like fracking tap water,
I can often hold a standard kitchen match to my water, and like I said, it is unpredictable, but the methane randomly travels with the water. and sometimes it will light quite spectacularly. Just like that.
So I would certainly call that a con of natural gas, is fracking will cause some people's tap water to light on fire. There's also been links that fracking can lead to earthquakes. They're certainly not powerful like city-destroying earthquakes, but there is seismic activity that comes from us basically pumping chemicals that sort of lubricate the layers of bedrock underneath certain areas. And sort of the last kind of con with fracking is that we don't really know what all these chemicals are. And by we, I mean common people and the government, because these companies have been working on fracking for decades. It's not really even a new technology. They've had it around since the 70s and 80s. And these gas companies have spent, billions of dollars developing this technology, teams of chemists working to develop them. And now that they produce this fracking material and it's working, the government's saying, well, okay, well, you need to tell us what's in those chemicals. And they're saying, well, we just spent billions of dollars developing this. We can't just give our secret away. Why would anyone ever invest in anything in the future? So I'm sure it's more complicated than that. I'm sure there are court cases going on. But at this point, there are certain chemicals that the everyday people in the government don't really know what's going on. So it's just kind of a big question. Let me quickly run through the types of renewable. I'm sort of running low on time here. Let me see what I have to get through. Pretty quick. Solar. So with solar panels, I should be more specific. These are also known as photovoltaic cells. Photo means light, voltaic refers to electricity. The basic idea behind this is you have your solar panel, and it's made of silicon. Now, if we look at the periodic table, silicon has 4 valence electrons. Now, what they do is they sort of contaminate. They call it duping. They dope it with certain elements like phosphorus, which have 5 valence electrons. So it's almost like if you have a whole bunch of puzzle pieces and they all have 4 sides and they all fit nicely, and then every now and then you put in one with 5 and it just kind of sticks out. Well, what happens is sunlight strikes those valence electrons that are kind of out of place, and those electrons are able to move down these sort of these lines. And this is obviously a very simplified way of explaining this, but all you need for electricity is the mass movement of electrons in one direction. So what ends up happening is electrons get bumped directly from sunlight. Sunlight hits them and they blast out, and they move down these lines. And generally what happens is they go to the other side of the solar panel, which has boron, which is kind of in between there. And if you look at the periodic table, how many valence electrons on boron? 3. So boron is almost like a 3-pronged puzzle piece in there. So it's like a hole. So the extra valence electrons from the phosphorus travel through these wires into the boron holes, and that's what allows electricity to flow. Overly kind of simplified way of saying they convert sunlight directly into electricity, which is why this is unique as one of the only ways of electricity generation that does not utilize electromagnetic induction. So let's talk pros and cons. Pros, once it's made, no greenhouse gases. Pros, renewable. Pros, don't rely on foreign material. Well, I shouldn't say materials in a sec. Does not rely on like foreign oil, anything like that. Now, some of the cons of this. They don't produce that much electricity. Now, you could get several of them on your house, and that will power your house successfully. But in order to power like a city, you need massive numbers of these. In fact, I have somewhere in my notes, you need something like 6,000 square miles of solar panels to equal like one conventional power plant. So you don't get a whole lot of electricity from these. Another con is that they only work when it's sunny. And another con is they often require rare earth metals, things that are very rare, tellurium, indium, cerium, metals that we never really mention in chemistry, but they're there on the periodic table. You can check. These are rare metals that are generally from China, and China kind of has a monopoly on them, and there aren't that many of them easily mineable. So it's tough to make these, is the point I'm trying to get at. It's also not that cheap. Right now, generally it's kind of a break-even type cost, where if you put them on your house, it's a big upfront cost and you probably will make that money back. And if you have a real good location, you're definitely going to make that money back, but there's a risk of it not really paying for itself. So usually what happens is the government will subsidize it because there are better, higher issues here like CO2. So those are the pros and cons of solar. Quickly talk about wind, which I've mentioned before. Wind turbines. The turbine spins, it causes a coil and magnet to move and generates power. So your pros here: renewable, no greenhouse gases, homegrown technically. I mean, they built these in America and it's good old American wind. The cons, things like it only works when it's sufficiently windy, and it can only work in certain locations. You know, if you put one of these in Wilton, it's never going to really spin. You got to put it in certain places that have enough wind. Other cons include the fact that it does produce continuous noise. Now, this is a huge point of contention. I personally have never been to a full-size industrial wind turbine, so I can't really comment on it, but people that live near them complain about the noise. Other people say it's nothing, I can barely hear it. It's just one of those issues that people will be debating. Other cons, they do kill a lot of birds. You could argue that the pollution from coal plants kills just as many, but it's just another fact. So, you know, there's pros and cons to everything. Anything else I should mention? Hydroelectric. I'll go over that real quick. Hydroelectric, it's the same idea. You have a lake and a dam, and you allow some water to flow through it and go into the river, and you put some kind of generator here, which spins a turbine, gets you electricity. A lot of good pros with this. No greenhouse gases. It's kind of local. You know, you don't have to ship anything from across the world. Generally low maintenance cost. Some cons with this: it's a huge upfront cost. It costs a lot of money to build a dam. It affects sort of aquatic life, specifically salmon always have a tough time, and a lot of major dams will have some sort of salmon ladder that literally carries the salmon up and dumps them. It can only be built in certain areas. You need the river to be kind of have enough water in it. So yeah, some pros and cons of that. And the last one I'm going to talk about is nuclear. Now with nuclear, you basically have the same setup. You have some kind of turbine and magnet coil, a coil and a magnet, and you have uranium, which acts as a fuel. Now uranium, you don't have to burn it. You literally just take a piece of magnesium, if it's enriched, and you just dunk it in the water, and it gives off so much heat that it boils it into steam. So let's talk about some of the pros and cons of this. Pros, biggest pro, no greenhouse gas emissions when it's in use, because you don't have to burn anything. It's just uranium. Another pro, incredible amounts of energy generation. It's one nuclear power plant powers an unbelievable amount of homes, businesses. Cons, and there are several. Cons include a huge upfront cost. To build a new power plant, nuclear power plant, you're looking at like $9 to $10 billion. That can't really be done without incredible loans from the government or from, you know, banks. Another huge con is that the fuel that you use, uranium, has to be stored for hundreds of thousands of years, anywhere between 100 and 500,000 years, which is just a time frame we can't even really fathom, because humans have only really had society for, you know, when was Mesopotamia? 10,000 years ago? I mean, the first steam engine was 200 years ago, and we're going to store nuclear fuel for 250,000 years? It's mind-blowing. Another con is that there is a risk of radiation leaking. Chernobyl was a big disaster, and that was mostly human error. The operators thought they could turn the plant off and then back on, and it kind of steamrolled out of proportion. Generally, what happens is once you start the nuclear reactor by putting uranium in, you can't stop that uranium. Like, there's nothing humans can do to stop a piece of uranium from giving off radiation. All we can do is constantly supply that radiation, that uranium, with something like cold water to cool it down. So if something happens to your cooling system, that's when you get problems. That's what happened in Chernobyl, and that's what happened recently in Japan. They had the power plant, was called Fukushima Daiichi Power Plant, like this. And being in Japan, they knew they had tsunamis, so they built a giant seawall to block oceans. They built it 30 feet tall. Unfortunately, when the tsunami happened, it was like 33 feet tall. So it flooded over the top and it flooded the bottom of the power plant. Not like they saw it coming, it's not like anyone was there to, get killed by this, but basically they had all this water that flooded the bottom. The problem was it flooded all of their cooling systems. So they now had uranium that was going and wasn't being cooled down, and it built up heat, so much heat that eventually it filled the kind of whole place with hydrogen gas from splitting the water, and it exploded, and it released a lot of uranium, radiation. Now, no one's died directly as a result of this, but there are kind of certain readings in things like fish where it shows high radiation. So there's a lot to consider with this. From an environmental perspective, most people agree uranium power plants, they're the way to go. The fact that they produce incredible amounts of energy with no greenhouse gases, most environmentalists can't envision a world that we don't rely on fossil fuels without nuclear. It's the only viable option. You can't supply this planet with solar panels and wind turbines. You can't make enough of them. Nuclear power plants, you can't. All right, I only have a couple minutes here. I'm going to quickly run through some of the statistics for Connecticut, which I think I have here. Let me start with USA. This is our sources for electrical generation in the U.S. 39% coal, 27% natural gas, nuclear, hydroelectric, wind, biomass, and oil. Biomass I didn't talk about. That's mostly ethanol. You take corn, you ferment it into alcohol, you burn the alcohol. So these are your big fossil fuels, 1, 2, and 1% oil. This is electricity. No, oil is generally not used for electricity because it's better to make gas out of it. Your renewables, that's your hydroelectric, your wind. Where's solar? Way at the bottom there. So those are still really coming to fruition. Let's look at Connecticut. 53% nuclear. How many nuclear power plants do we have that gives 53% of the state? One. It's in Groton and it powers over half the state. That shows how powerful nuclear reactors are. A lot of natural gas in Connecticut as well. Everything else very small. 0% wind. No industrial wind turbines in Connecticut yet. Last thing I'm going to show real quick. Connecticut has a pledge. It set a pledge that, nope, we're not going to have time for that, that by 2020, 27% of this state's energy would be renewable. What are we at right now? 3.5%. What was our goal? For now, it would be, I believe, somewhere around here, 18%. So Connecticut's fallen way behind that. All right, that's it for this video.